Hi all, welcome to another session of electrical engineering. Today I'm going to take a lecture on the topic testing of DC motors. I am Gayathri, Assistant Professor, Triply Department, Mahaguru Institute of Technology. Let's start. The main contents of this presentation are the various testing methods of DC motor. Broadly, they are classified into two types, direct test and indirect test. The indirect test is again subdivided into two types, Swinburne's test and Hopkinson's test. So, before entering deeply into the portion, first we have to know why these tests are required. The tests are mainly conducted on the DC machine to judge its performance. Basically, in every machine, tests are mainly doing to conduct its efficiency and as well as to determine its performance for various applications. The efficiency of a DC machine depends upon its losses. Smaller the losses, the greater is efficiency and vice versa. First of all, we have to look the basic formula of efficiency of a machine. Efficiency is the ratio of output power to the input power. The input power can also be rewritten as the combination sum of output and losses. So efficiency is the ratio of output to output plus losses. Efficiency can be found out by the following tests. First one is the load test, second is Swinburne's test, and third is the Hopkinson's test. First, we will discuss about the direct method. Direct method involves the load test. This one is the pictorial representation of load test. This is a common method. We are always doing this method in our electrical machines lab, and which one is the simplest format of calculating load. Figure shows a pulley drum arrangement. Here H1 and H2 represents the hand wheel which is used to put different loads in the spring truss, which is shown by S1 and S2. The round portion is the brake drum which has a radius of small letter r. In this method, a water-cooled pulley mounted on the motor shaft. First, we will calculate the no-load reading, and after that, a set of values were given to the motor through the spring masses. Thus, efficiency can be found out directly applying some sets of equations as follows. These are the points previously discussed. First one is which is suitable for small DC motors, and this load test is also known as brake test for DC motors. The belt pulley arrangement attached to spring balance S1 and S2. Loads on the pulley is adjusted by hand wheels H1 and S2. From here, we can get the shaft torque which is developed across the motor. The shaft torque is given by the equation TSH is equal to S1 minus S2 into R into 9.81, where S1 and S2 are the masses which formed in the spring trusses 1 and 2. And R is the brake drum radius of the motor, and 9.81 is the gravitational constant. The shaft torque means the net torque or the net pull which is applied across the rope itself. Then we have to calculate the efficiency. For that, first we should calculate the output power. An equation for calculating the output power is there, which is given by 2 pi n TSH divided by 60, where n indicates the rotation of rotor or the speed of the rotor. The input power, we know that the input power is the product of supply voltage and current, and then output power. We are supplying this output power's equation here. then output power is equal to 2 pi n. Sorry, we are substituting the value of TSH in output powers equation. So 2 pi n into S1 minus S2 into R into 9.81 divided by 60. As we seen from the previous slide, we can write the input power as the product of supply voltage and a current V into I, and the output power can be rewritten as from that previous slide itself. We wrote this equation 2 pi n into S1 minus S2 into R into 9.81 divided by 60, where n indicates the speed of the machine. Thus, efficiency can be written as by using the basic formula output power by input power 2 pi n into S1 minus S2 into R into 9.81 divided by 60 Vi. Coming to the disadvantages of load test, the main disadvantages in the case of load testers are this method can only be used in case of small motors. For heavy duty motors, we cannot use this method. And the spring balance readings are not steady. We are using only by manual means. Because of this, some miscalculations were occurs in the case of spring thrust readings. Because of these drawbacks, we are going for the indirect method. Next is the indirect method. Mainly in the indirect method, the first method is Swinburne's test. The pictorial representation of the Swinburne's test is shown in the figure. First of all, we have to know that it is a predetermination test. Predetermination test means tests are mainly two types: a determination test and predetermination test. If we are applying the load directly and calculating the machine performance, then it is known as a determination test. And if we are not giving any load to the machine and we are calculating all the performance, then it is known as a predetermination test. And it is also a no load test. In this method, the DC motor runs at no load and the losses were determined. Once the losses are known, its efficiency at any desired load can be easily found out. It is the most common and simplest method of testing of shunt and compound DC machines. Here in figure, A1 represents the ammeter which measures the no load current, and A2 measures the shunt field current. That means the current which is offering by the field of the motor. Then this one shows the starter. We know that always we are starting the DC motors by means of a 3-point or 4-point starter. This one shows the 3-point starter, and this is the armature of the DC motor. And here R is the regulating rheostat which are mainly using, and this is the field connection. So as we said earlier, it is the most common and simplest method for testing shunt and compound DC machines. DC machine means DC motors. Shunt, we are using this tester for both the shunt motor and compound motor. This method runs at a no load and the losses are determined. Once the losses are known, its efficiency at any desired load can be determined easily. These are the calculation of efficiency equation. Here V is the supply voltage we are giving. I0 is the no load current read by the ammeter A1, and ISH is the shunt field current read by the ammeter A2. No load current IA0 can be written as I0 minus ISH. From that figure we can write all these equations. So the no load armature current IA0 is I0 minus ISH. I0 is the no load current and ISH is the field current. Then no load input power of the motor can be written as the applied voltage and no load current I0 V into I0. Thus no load power can be determined by voltage into current equation. Here voltage is the supply voltage and current is the no load armature current Ia0. So the no load power input to the armature can be written as V into Ia0. Ia0 can be rewritten as I0 minus ISH. Substituting this value here, then no load power input can be written as V into I0 minus ISH. In Swinburne's test, no load power input is only required to supply the losses. The losses occurs in the machine are mainly the losses occur in the case of conducting Swinburne's test are iron loss, armature copper loss and friction windage loss. Iron loss is always occurs into the core. Copper loss occurs in the armature and winding. Friction and windage losses are the mechanical loss which occurs in the mechanical parts of the machine. By using different sets of equation, we can calculate the efficiency directly. So the armature copper loss, we know that the copper loss is always I square into R is the copper loss equation. Here the input current is armature current is Ia. So the armature copper loss can be written as Ia square into Ra. We already find out the relation of Ia, that is I0 minus ISH. So so armature copper loss or Ia can be written as I0 minus ISH square into Ra. Then again we are determining the constant loss. Mainly constant loss is the sum or combination of the shunt field loss, iron loss and frictional windage loss. So we can directly calculate the constant loss by subtracting the armature copper loss from input to the motor. So constant loss can be written as WC. WC is equal to input to the motor minus armature copper loss. Input to the motor, in the previous slide we have found the input to the motor, that means input power to the motor as V into I0, and also from the above equation I0 minus ISH the whole square into Ra is the armature copper loss. Substituting both these values we can find out directly the constant loss occurred in this test. So WC, the constant loss can be written as V into I0 minus IH the whole square into Ra. Therefore total loss is the summation of copper loss and constant loss. Thus we can directly add these two equations, that means the equation of constant loss and also copper loss. Thus total loss is the summation of copper loss and constant loss. Copper loss is I0 minus ISH square into Ra and the constant loss is WC. So we found out the copper loss and we found out the constant loss, copper loss and total loss. Thus efficiency can be found out by using the basic format output power by input power. Output can also be rewritten as input minus losses. So efficiency is by applying these combinations of equations. We can write the efficiency as Vi minus I0 minus IS square into Ra minus WC is the constant loss whole divided by the input power V into I. So this is the simplest no load test which is conducting in case of a DC motor, and which one is the simplest format for determining the losses and efficiency of the DC motor. Now we have to look. Coming to the advantages and disadvantages section of Swinburne's test, first we will look the advantages. The main advantages are this test is very convenient. That means it can readily calculate the values because this test is mainly doing at the no load itself. So we can readily find out the values easily. Then it is a no load test. The power required to carry out the test is very small. Efficiency can be determined at any load because the constant losses are also known. The main disadvantages involved in case of Swinburne's test are the test does not give an accurate efficiency of the machine. It is because the iron losses under actual load is always greater than those measured. It is mainly due to the armature reaction effects which involves in the case of a DC motor. Because of the presence of these armature reaction drops, the iron loss under normal condition is always greater than the no load condition. And next is the test does not enable to check the performance of the machine on full load. Coming to next method, which is a Hopkinson's test. The main advantage of conducting this test is it is more accurate compared with other tests. In order to carry out this test, we require two identical DC machines and a source of electrical power. One of these two machines are operated as a generator to supply mechanical power to the motor and other operate as a motor to drive the generator. This process of back-to-back driving of the motor and generator, Hopkinson's test is also called a back-to-back test or regenerative test. This one is the pictorial representation of Hopkinson's test. These two green picture shows the motor and generator set. The yellow portion is the coupler which is mainly used to connect these two identical machines to carry out this test. This is a pictorial representation of Hopkinson test. Here M act as a motor and G act as the generator. Input to the motor is given by the supply with the help of a 3-point starter. M work as the motor. The switch is kept open. Here this switch is kept as open. The field current of motor is adjusted with the motor field rheostat. Here it is the field of motor. This field current I4 is adjusted by means of the motor field rheostat, which enables the motor to run at a rated speed. The machine G acts as a generator. The machine G means this one. Machine G acts as the generator. Here it shows the generator field winding, which is mechanically coupled to M, which is mechanically by this coupler. This both motor and generator coupled. So the motor runs at a rated speed by means of this regulating rheostat of the field of motor. Thus by the coupler itself the generator also work or run at a rated speed. The excitation of the generator is also adjusted with the help of generator field rheostat. When the voltage of generator equal to the supply voltage, the main switch is closed. Thus both the machines are now run in parallel across the supply. That means when the switch is closed, both the motor and as well as generator will run parallelly. And this condition is known as floating of generator. The same thing is explained once more here. The mechanical output of the motor drives the generator and electrical output of generator supply input to the motor. Thus output of each machine act as an input to other machine. That means motor and as well as generator act equally input and output to both the machines. This format or this process is known as regeneration. Because of this only concept, our test is also known as a regenerative test. Both supply voltage and generator voltage become same and the machine will run parallel, and thus the generator is said to be in floating state. Float or floating state. Float means the generator is neither taking nor giving any current to the supply. So we are calculating the efficiency by two cases, assuming first one is both the machines have same efficiency. So First we have to calculate the motor output. For calculating the efficiency, we know that the basic formula eta is equal to output divided by input. So efficiency can be written as output by input. We know that output can be written as efficiency into input. Same function is also here we applied, so that motor output can be written as motor output is equal to efficiency into motor input. Then we are looking into the motor portion. In this motor portion, the entering current is I1 plus I2. So the input current can be represented as I1 plus I2. Motor input is the product of voltage and current. So V is the supply voltage we are applying. So V into I1 plus I2 into this efficiency eta. Motor input is directly equal to the generator input. As we said earlier, the motor output is directly feeding the generator input by the process of regeneration. So the generator input is always same as that of the motor output. Then we can go into the generator output equation. Here also we can rewrite in the same manner, eta into generator input. Here we found the generated input as eta into V into I1 plus I2. Here we are applying that equation and we will get eta square into V into I1 plus I2. But generator output is, by looking into the generator portion, we can directly write that the output of generator is the supply voltage V into the generator current I1. So equating both the similar equations, we can find out the value of efficiency eta is equal to root of I1 divided by I1 plus I2. Considering the second case or the next case, assuming that iron friction and windage losses are same in both the machines. That means we are assuming the losses are same. That means iron friction and windage losses are same for both that identical machines. Then we are calculating the efficiency again. Here also we are taking that picture for reference. Ri is the armature. We know that Ri is the armature resistance, and I3 is the field current of generator, and I4 is the field current of motor. Then armature copper loss of the generator can be written as, we know that copper loss is the product of I square and Ra. I square is the armature current and Ra is the armature resistance. Here we are considering the generator. So the upcoming current or the armature current in the generator is I1 plus I3. So armature copper loss can be written as I1 plus I3 the whole square into Ra, and armature copper loss of the motor can be written as I1 plus I2 minus I4 square into Ra. Minus I4 means the shunt field branch also considered. In the case of motor, the current is entering into the armature and the entering current is I1 and I2. So I1 plus I2 minus the leaving current, that means the shunt field current is also taken in account. So I1 plus I2 minus I4 square into Ra. Shunt copper loss of the generator is means the shunt field losses. Shunt field means the parallel branch connection or the field connection. Field connection of the generator. Here that current of the generator is I3 and the voltage is a constant voltage, that is supply voltage V into I3, and same as that of in case of motor. For the motor, the field current is I4. So the shunt copper loss is the product of V into I4. The total power drawn from the DC supply is V into I2, which is equal to the total loss of the motor and generator. VI2 is the total loss of motor generator. That means we are combining the effect. That means for generator and as well as the motor, we are taking in account of these two losses. And then we are concluding it as a total losses of both the machines. So the total loss of the both machines is V into I2. By applying this equation, if we subtract armature and copper loss of the two machines from V into I2, we get iron friction and windage losses of the machine. So therefore, iron friction and windage losses of the machines of motor and generator can be found out by subtracting the total losses from the total losses, other losses that we are uh, already we are calculated here. These all losses are subtracting from the total losses for finding out iron and friction losses. Thus we will get uh, W. We are named those losses as this much of loss we are renamed as W. Therefore, iron and friction windage losses of each machine is W by 2. W is the total loss. That means for both motor and generator, the total loss formed is W. We have to consider separate machines. For that, the iron friction and windage losses of each machine is represented as W by 2. Thus, we can calculate the generator efficiency and motor efficiency separately. Output of the generator, we know that V into I1, and the total loss is the summation of W by 2. W by 2 is the friction, windage and iron losses of generator. That is, this 2 means for two identical machines, W is the total loss, but we are considering each case, so we are taking W by 2. W by 2 plus I1 plus I3 square into RA plus VI3 is equal to WG. So the total generator efficiency is equal to output power divided by combination sum of output plus losses, that is Vi1 divided by Vi1 plus Wg. In the case of motor, input to the motor can be represented as V into I1 plus I2. Total losses can be represented as I1 plus I2 minus I4 square into Ra. It is the armature copper loss. Vi4 is the shunt field loss, and W by 2 is the friction iron loss, which is equal to, we can say, Wm. This motor efficiency can be rewritten as input minus losses divided by input, which is equal to V into I1 plus I2 minus Wm divided by V into I1 plus I2. These are the calculations involved in case of Hopkinson's test. Next, we have to go on the advantage and the disadvantage portion. The advantage mainly included in the case of Hopkinson tests are the total power required to test the two machine is small compared with the full load power of each machine. So the total power required, it is a regeneration test. Because of this, the total power required should be almost constant for each machine. The machine can be tested under full load condition so that commutation quantities and temperature rise can be checked. Here, by using this Hopkinson's test, we can calculate the efficiency, temperature rises and commutation qualities also. Then it is more accurate to measure. All the measurements are electrical, which are simpler and more accurate than mechanical measurements. Then coming to the disadvantage, we know that we are taking two identical machines. By for taking these two identical machines, the cost is very high and the circuit will become always complex. Okay, that's all about this session. Thank you for watching. Thank you.